pleasure to be here, but it's also a great pleasure to celebrate the birth of ANSER. It's just a wonderful opportunity for all of us who like to work together to have the wherewithal to work together a lot more and to bring in lots of other collaborators. I think you've seen this slide already, so I'll go over this part really quickly. But we've got this enormous problem, this insatiable demand for energy. There was an article in editorial by Thomas Friedman in the New York Times last October where he pointed out that the US economy was being kept afloat by borrowing money in China to spend in Saudi Arabia. And you know that that's an unsustainable situation. And to get out of it by having a depression is not the right way to do it, obviously. The other part of the equation is even if we did have infinite supplies of cheap oil, do we want to keep putting carbon dioxide into the Earth's atmosphere the way we are? And obviously, we're risking big changes in our climate. And so what are the options? Well, as Harry pointed out most eloquently and other speakers, there's so much free sunlight. There's enormous amounts of energy. We just have to learn how to harvest it. And the two ways you can think of are solar fuels and solar electricity. Now, some people, critics of these kinds of things, have said, well, you guys don't have a plan. You don't even know what to do and how to solve it. Well, I would argue just the opposite. There have been groups of really the best minds worldwide brought together to worry about these problems. And in fact, there is a plan. There's a really, really good plan of all the options that have to be followed and all the research that has to be done. And I think we're all happy that it looks like we're moving forward along that plan now. So let's talk a little bit about solar energy conversion. And one way we've heard of already, and Tom gave us a beautiful lecture on photosynthesis, and Gary as well. So that's one option, certainly important. I don't think there's one answer to this problem. There's not just one right way to do it. Harry told us all about water splitting. We heard some of this from Gary as well. Really good prospects here in both areas. And the other one, which Renee gave us a beautiful introduction to, is photovoltaics. And this is what I want to talk about today. I want to talk about it, approaching it from a slightly different way. Now, so let's say something about inorganic versus organic photovoltaics. The options of inorganic, and Harry again gave us some beautiful metrics. Silicon is really robust. It's expensive to make, it's rigid, it's expensive to install, but it has very nice power efficiency and very good durability. There are other lower cost inorganics on the horizon, and one of them is SIGs, one of them is cadmium telluride, and then the first solar people are talking numbers that look really exciting, and amorphous silicon. And what all of these have going for them is very low cost, high throughput manufacturing, the ability to put it on flexible backings. There's another wild card out there, and that's the one I want to talk about, and Renee talked about already, and that's organic. Right now, we don't have the power efficiencies of silicon. We need at least 10%. But the pluses are very high throughput manufacturing. Imagine printing solar cells the way you print newspapers. Inexpensive materials, mechanically flexible, tailorable properties. And the other attracting thing is to integrate these materials with building materials. So in a new house, the shingles would have already installed in them solar energy generating capacity. The other intriguing thing about organics is the possibility of some real step changes, some real breakthroughs. I don't see those here. I think these will continue to evolve. But here there's a chance to really do something completely different, completely out of the box, completely off the wall. And I think for people who make materials and try to understand them, and with a long-term view, and we're really going to need a long-term view for these problems, this is really interesting. So let's say something about how an organic solar cell works, and it's sort of building on what Rennie talked about already. There'll be some transparent conducting electrode because we have to let light through. We'll talk more about that. There has to be some sort of layer against this electrode that compatibilizes the rest of the active structure with the electrode for a whole bunch of reasons. Everything from planarizing to adjusting work functions to smoothing the differences in surface energy. There'll be a p-type donor material and an acceptor, and then a low work function metal cathode. So this is the anode, and this is the cathode. So the challenge is, number one, if I introduce a photon, is to capture the maximum solar output. In principle, we ought to know how to do this. The second thing is, which Renee talked about already very beautifully, is this bound hole pair then has to separate, and this has to have a high efficiency. And ideally, as we heard already, if we need a very large energy drop to do this, that's very inefficient. But we have to then create these excitons which live long enough now to begin to migrate toward their respective electrodes. So they have to get across a number of interfaces. And ultimately then the energy, the electrical energy, will be harvested. They have to get across this interface, this one, that one. And that, as we'll see today, is one of the great challenges, and maybe one we haven't thought enough about. Well, this is pioneering work, and I don't know, maybe I'd have to talk to Heger and Richard Friend. Was it really planned or an accident? But you mix these donors and acceptors together, and you get something like a bowl with two different kinds of pasta in it. And one conducts holes and one conducts electrons. And this is called a bulk heterojunction solar cell. And this is a typical structure of one. So here's the anode, indium tin oxide. Indium tin oxide is awful stuff. It corrodes. Indium is scarce. It's not an earth-abundant material. It certainly doesn't have the conductivity we need. And then on top of it, the interlayer that's usually used is something called PDOT, which is a conducting dope polythiophene. It's got a pH of about 1. It will corrode the ITO. It's electrically inhomogeneous. It's really not a solution. It's a suspension. If ITO is bad, PDOT is even worse. Yet, as we agreed on at lunch, nobody seems to have anything better. How much does this limit the performance? I'll talk about that. And then here's our blend. Here's lithium fluoride, usually put here, and there's about 6 different theories why you need lithium fluoride, other than that it helps, and then the aluminum cathode. The subtleties of the microstructure are beautifully illustrated. Here's results for 2 different cells, and all that has been changed is the solvent that's cast the film from toluene to chlorobenzene, and you can see the efficiency goes up almost by a factor of 3. It has to do with the microstructure, has to do how these materials phase separate. And so the kinds of questions to ask is just how important are all these interfaces? Is there something better than PDOT, and is there something better than ITO? And that's basically what I want to talk about this afternoon then. So first of all, we're going to talk about interfaces, and I'm going to start from a rather different viewpoint than the other speakers. I'm going to start with organic light-emitting diodes and polymer light-emitting diodes and ask, has all that the community learned about these, are they going to help us? And then we're going to talk about interfacial layers, and we're going to talk about both organic and inorganic interfacial layers. If we have enough time, I want to talk briefly about how you might think about capturing more of the solar spectrum, and actually to say, well, maybe polymers are certainly one option, but maybe polymers are not the only option for making solar cells, and there's some arguments why maybe we should be using small molecules. Then I want to end with a little provocative crystal ball gazing and some modeling that Mark Ratner and I have done. So let me begin with an organic light-emitting diode. And I would say if I had showed this to an audience 10 or 15 years ago, they'd say, that's going to be the biggest joke of all, that you're going to make a display using organics. And the way they work looks very much like, in reverse, a photovoltaic cell would work. And so we'll have either a sandwich, and this is basically a Philips technology, and a Uniax DuPont display technology, a cathode. Here's ITO again, except that we're going to inject electrons from the cathode and inject holes from the anode. They find each other. They don't always find each other, but when they find each other, they recombine, they form an exciton, it decays and gives off light. So it looks a little like the inverse of the photovoltaic cell. There's another technology which is Kodak, Sanyo, a large number of Japanese and Korean companies universal display, which uses vapor-deposited layers of small molecules. This is the polymer here. But the idea is basically the same. Electrons injected from one side, holes from the other. And what we always hope is that the holes and electrons will find each other, recombine, and give off light. We'll get into this issue of suppose they don't, and how easily do they traverse those interfaces. So you might say, well, this is just a pipe dream. I mean, no one's ever going to really make a display with an organic. This is one of the most impressive examples. And for the locals, if you go to the Sony store at Old Orchard, you'll see one. It's spectacular. The color richness is nothing like an LCD display. The screen is 3 millimeters thick, very, very high efficiency. And then you say, well, yeah, but they probably only last a couple hours, right? If you go to Novaled's website, the latest kinds of numbers, and these are simulated because you obviously can't do an experiment for 10 to the 6th hours. It's a very long time. But you do accelerating testing, and they're producing OLEDs which have estimated lifetimes on the order of 1 million hours. So the idea that organics are necessarily fragile, they poop out, they die, is not true. It depends simply on the molecule, how it's prepared, and how it's processed and put into the device. So there's nothing intrinsically wrong with organics to do optoelectronics. So a little bit of history. So my group got started in it, and our first thought was, well, let's, as one always does, let's see if we can duplicate the literature. And the student who was doing this work put TPD, which is a whole transport layer, in an ALQ, and started making these sandwiches. And at one point, after putting the TPD down, he thought, gee, you know, there may be some water on the ITO. Let's warm it up a little and pump on it. And what he discovered, to his horror, was that the TPD de-wetted. Why? There's a terrible surface energy mismatch. You put something very hydrophobic on something very hydrophilic. And in fact, this was the problem with the first generation of Motorola OLED phones, which you can only buy now on eBay because they were all pulled off the market. And it had to do with the fragility of this interface. So Kodak attacked that by using copper phthalocyanine and other kinds of interlayers. They don't really work terribly well either. What this student Ji Tsui did was he took the TPD architecture and fastened onto it 2 linkers so he could covalently link it, bind it to the ITO anode, to this oxide anode. And then you don't see any de-wetting at all. Ji made some devices. These are early devices from our lab, but the important thing is, in terms of electroluminescence, quantum efficiency, response to thermal stress, which meant Ji put it in the glassware oven for half an hour, you found a remarkable ruggedization of this multi-layer structure with just a few angstroms of this interlayer. Now you can do some physics. This is called a hole-only device. So we're going to compare devices where it looks a little bit like an OLED, but there's a layer of gold there, and that blocks electron injection. So all you measure, it's called a hole-only device, is hole injection across this interlayer, and then we varied the material in this interlayer. And so this is copper phthalocyanine, and this is the current density. This is bare ITO, and then these are 2 different organic self-assembled injection adhesion layers that we synthesized. You can see a tremendous increase in the flux of holes flowing across this interface. And you sort of say to yourself, this must have some implications for if I want to make a photovoltaic. In that case, remember, I want to extract holes in electrons. So you can make you can synthesize a whole library of these materials. And of course, when they're on the surface, we characterize them by everything from cyclic voltammetry to X-ray reflectivity at the argon synchrotron. What you see, which is most intriguing, is this is the material I talked about so far. This material, which has 4 legs, which places the pi system of the TPD right up against the ITO band structure, whatever that may be, has a much greater current density, and the OLED has a much greater luminance. So the intriguing thing here is there are suggestions for how you might modify this kind of the OPV structure for just the same purposes. This is Henry Yan's work, and this takes it one step further. These are some polymer light-emitting diodes, and what Henry compared was the performance of one that's got a cathode, an emissive layer, PDOT, and ITO with the same structure, where he vapor deposited just a few nanometers of this material, because this material has a very high lying LUMO. It's been used as an electron blocker. And what do I mean by an electron blocker? Well, I blithely assume that the holes in electrons come from opposite directions in the OLED, meet, and give off light. Suppose they miss each other. Well, if the electron gets to the anode, I've wasted a lot of energy. So the thought was that if this blocked the electrons from getting to the anode, they would wait and help suck in more holes. And in fact, it works beautifully. So this is light output, this is current efficiency, and you notice in each case, with the electron blocking layer, you get a much higher efficiency. And one of the implications is that PDOT, among all its failings, electrically inhomogeneous, corrosive, all of that, also is not nearly as good an electron blocker as a lot of people thought. So Henry reasoned, if this is true, let's take it one step further. And this is a device that now has a really optimized emissive layer. And what we concocted, or what he developed, was a blend where we take the TPD Si2, remember this was our injection layer with chlorosilane groups, and we mix it with a good hole conducting polymer, and in air, on spin coating, the chlorosilane groups cross-link, and so we make a very dense polymer. It's covalently bound to the ITO. It has a hole mobility of about 10 to the minus 3. It's optically transparent and very robust, and it makes very nice polymer light-emitting diodes. So without triplet sensitizers, we had 17, 18 candelas per amp. So you can make a very good polymer light-emitting diode with just a few nanometers of this. So then you then ask, what would happen if I started taking some of these materials and approaches to a photovoltaic? And so here's our idea. This is a long-range idea. This is what ANSER is for, is to attack long-range problems. Suppose you made a photovoltaic, and it'll be a bulk heterojunction one, except I'm going to include the option of electron blocking layers to prevent stray electrons from leaking out. You see, I think in a bulk heterojunction material, if there are a lot of dead ends, if there's a lot of PCBMs sticking right up against the anode, we're likely to have electrons leaking over. Likewise, the photoactive layer, obviously we're going to need that. You can imagine by the same kinds of approaches putting in a hole blocking layer. New TCO materials as alternative anodes. I'll get into that. As I said, indium's in short supply. Charge blocking at the interfaces. And ultimately, we want a cross-linked multi-layer structure here. Now, I'll tell you more about that at the end, and interfacial stabilizers. So our first set of experiments, the game plan was to use known bulk heterojunction materials. We're going to use two that René told us about already, the polyphenylene-vinylene system and the polythiophene system. And we're going to keep those constant and turn on other aspects of other parameters that we want to introduce. One of the things you learn when you do this, which people in the field, when you think you've got something really, really pure, you've just started. So you really have to spend a very large amount of time getting these materials pure. And don't think you can buy something from Aldrich and they claim it's 99.99% pure and that means anything at all. So it's very, very important to get all the impurities. The other thing is you have to have proper instrumentation, and I think we've got that. And you have to have the instrumentation calibrated by NREL. There are lots of numbers in the literature, and sometimes you worry about how exactly they were measured and how reliable they are. So you have to have good instrumentation. You have to have it calibrated by NREL. And for your very best cells, you should go to NREL again and get them calibrated. We already talked about the solar spectrum. And of course, as René already pointed out, neither of these materials is terribly good for capturing a large swath of the solar spectrum, but they're good materials to test some of our ideas about interfaces. So the first experiment we're going to use then, is take this TPD Si2, this blend. And remember I said we can spin coat this, it cross-links in air, we do a gentle anneal, and it's ready to go. And we're going to use about 10 nanometers of it, and it's got a mobility, as I said, about 10 to the minus 3, 10 to the minus 4. This is the whole mobility. It cross-links in air. It's very, very insoluble. And this is one thing to think about. I mean, your first thought may be, oh, let's make this polymer light photovoltaic. I'm going to spin coat all these layers on top. Wait a minute. Maybe the second layer you spin coat on is going to dissolve the first one. So you need orthogonal solvents, which can be really, really difficult. So with PDOT, you use an aqueous solution, or you have something that's densely cross-linked and becomes insoluble. So we'll do that. And then the next is, well, before that you look at the energy levels, and some of these are measured by electrochemistry or UPS, for ultraviolet photoelectron spectroscopy, because we don't want to get into something where if the levels are not aligned well, we'll get a very non-ohmic contact. And so this TPD Si2 looks very good to match with this particular bulk heterojunction material. And so this is some work of Alex Haynes. And so this is the control. And I know that Shaheen gets 2.5, but most of the literature is closer to 1.5 or 1.7. And that's what we can get. And this is the material we're going to completely do away with the PDOT. So we're going to take this terrible stuff away, $100 for a little bottle of stuff that it's a few milligrams of PDOT inside, and we're going to do away with the PDOT. And you see, and Rennie showed already very nicely, when these plots start looking very, very square, that's a good sign. And so we get an efficiency of about 2.3%, so much better than our control with PDOT, good fill factor, good short circuit current. And I'll come back and say one other thing. Now you might say, well, to really do a proper control, you should use both PDOT and this electron blocking layer. We do that, and it's interesting. You get a very high open circuit voltage, but the reason is you've essentially put in a Schottky diode. Look at the slope here. So you've got a lot of series resistance, and the current has not improved any. Then what Alex did is he took all 3 cells and put them on a hot plate for 1 hour at 60 degrees C. And only one of the cells actually survived. The others degraded quite remarkably. Another experiment we did, I think Alex Martinson is in the audience, so Alex, and Alex is a student of Joe Hupp's. So we did an experiment which is like an impedance experiment. It's called intensity modulated photovoltage spectroscopy, IMVS. And so what you do is you have a light on the cell, but on top of that there's another pulsed light, and you can measure the lifetime of the carriers. And when Alex first got this data, or both Alexes got this data, it was really pretty remarkable, because the lifetime of the carriers, and our interpretation has to do with recombination at the interface, increased dramatically. And we've since done a lot of other experiments, and they're all in line with the picture that the longer carrier lifetime is associated with reduced interfacial quenching right at the interface by coating the ITO with this layer. In fact, we've seen the same thing in OLEDs as well. So then you say, well, okay, so the PPV systems are interesting, but let's get to something which has a higher power conversion efficiency. So now we're going to switch and look at this polythiophene C60 material, and this is well developed in the literature. These are what the energy levels look like. And it turns out that this particular material is not well suited for this particular hole injection layer. We've now got one that it is, but this one, it doesn't have a good matchup of the energy levels, and we can show that in lots of measurements. So we thought, let's really try something out of the box. for a layer that will extract holes and block electrons. And the benchmark, sort of our competition, or what we've got to better, this is some very beautiful work by Yang at UCLA, and we heard it mentioned already. And basically, again, all he did is take this material and try different annealing protocols. And when he hits it just right, you can see here a nice square, relatively square. So he's getting a short circuit, an open circuit current of about 10 milliamps per centimeter squared, and an open circuit voltage of about 0.6. And here's the external quantum efficiency, and it's about almost, say, 68 or 70, and an efficiency of about 4.37. We worked like hell, and we can get to about 4. We haven't been able to get higher than 4, but let's assume, so in our hands, we get 4. So what could we use then as an extraction electron blocking layer? And we decided to look at some oxides. We decided to look at nickel oxide, and it's a p-type semiconductor. Thin layers are quite transparent and visible. They're just some small DD transitions. We grow the films, we meaning Bob Chang, my colleague in material science, grows the films by pulse laser deposition. It's a very good growth technique, exploratory growth technique for growing a film of anything on anything. I think that's a fair statement. In terms of nickel oxide, it's got a rock salt structure. I would say you can find easily 20 papers in Physical Review B, all 20 pages long, on its electronic structure, because it's a highly correlated material. And that's sort of something aside from what the discussion is this afternoon. But the other thing is, if you match up the energy levels, nickel oxide matches up, the Fermi level matches up very nicely. We should have a relatively good ohmic contact, and the conduction band is very, very high. And all of those say it's going to be hard to get electrons leaking back to the ITO from our active layer. And so these are different film thicknesses that we grew. And let's make some cells. So first of all, nickel oxide deposited on ITO, the AFM, and now we have conducting AFM as well, says that if anything, it planarizes the ITO. So the RMS roughness of the ITO drops from about 4.8 nanometers to about 1.5. Let's look at some cells. And so what we're doing here is going from a very, very thin nickel oxide coating. And let me put nickel oxide in quotation marks, because you're probably asking, how do you know it's really nickel oxide? And you can see as we make it thicker and thicker, at very thin layers, we get these very, very nice square plots. And you can see that the short circuit current is greater than Yang's. The fill factor is greater than his. The open circuit voltage, he had about 6. Well, I can go back and look in a minute, but these are all higher than his. And the power conversion efficiency is about 5.2 for the 10 millimeter device. And so then you get really worried that did we do something wrong? And so you go to NREL, the National Renewable Energy Lab, and they have a calibration laboratory there. And on one of our cells, they got the same cell. They got 5.6% efficiency. So that's pretty good. Now, you should ask a lot of questions. What is the external quantum efficiency? And this is what we get, and I think Renee may have asked me in Boston whether we might have seen some reflection effect. We're still worrying about that. But whatever it is, we've made essentially the same cell that Yang has, except we put in this 5 or 10 nanometer nickel oxide layer. And you can see we're above 80%. And just as an aside, Mark Ratner and I and a student, John Cervantes, I don't know if John is here or not, there's a modeling paper we've done, and we basically concluded that at this level, this is about, and it agrees with what Renee said this morning, this is about all the current you're going to extract out of this particular cell. The intensity modulated photovoltaic spectroscopy says that, again, the carrier lifetimes are increased, work with Joe Hupp, just as we saw in that other case. So then you say, well, how the heck do you know? Is it nickel oxide? Could it be some sort of other nickel phase or indium phase, indium nickelate, nickel indate, whatever? And so this is work with Bob Chang. And down to the nanometer level, these are the lattice fringes of a face-centered cubic material. And everything agrees with nickel oxide. And so this is the ITO, here's the PCBM. Electron diffraction, again, looks like nickel oxide. Well, you say, yeah, but you've just gone to one crystallite. So this is work with Mike Bedzik, another colleague in material science, and this is at the APS, the Advanced Photon Source at Argonne, and these are films grown on float glass. The trouble is that the ITO is too large a background, but what you can see in float glass at 5 nanometers of nickel oxide grown the same way, all of the signatures, and this is another one here grown in Bob Chang's lab. It clearly is nickel oxide, and you can even calculate the crystallite sizes and do all of that. So then you say, well, what about the work function? What do you know about that? And if I want new inorganic interlayers, how do I predict that? Well, we're delighted to have as a colleague Art Friedman, and these are calculations done with his student Dr. Song. And so this is a technique, it's a muffin tin technique, but way beyond that. So full linear augmented plane wave calculations. And Art calculates for 9 layers of nickel oxide. Here's the electron density on a surface. He calculates a work function of 5.62. And then Ben Lever, who's a student with Mark Hersom, jointly with myself, and actually Mike Durstock at the Air Force Laboratory has a very fancy photoelectron spectrometer, and they get 5.040 for the work function. Art gets 5.62. The nice thing here is we're really going to be well equipped to design new materials. And another really interesting thing is what happens now when you do a calculation with a layer of organics covalently linked to that surface. And that's one thing we'll do under ANSER. What about lifetimes? You might worry about that. So this is the work of Michael Irwin, and we worried about that a lot. Like lots of organic optoelectronic materials, frequently there's a break-in time, and then it levels off. And I'm happy to say now we've had a cell running for more than a year, and there's less than 5% decay. It's encapsulated, of course. Let me just do a quick diversion to bring up one interesting issue. You know, polymers are hard to make. Polymers are hard to purify. Polymers are not monodisperse. So what about small molecules? Steve Forrest has got some really interesting results with vapor-deposited ones, but I want to print them. I want to do them on a large scale. So here's a collaboration with the Pagani group in Milano, and Giorgio's group has been making a number of squarenes, and one of the things that struck them was the optical absorption, especially as a film, is very, very broad, very large extinction coefficients, just where you want it. You can make, and the energy levels versus PCBM. In principle, we ought to get a really nice open circuit voltage. So let's look at some first generation cells with PCBM. And what you see are fairly large open circuit voltages, quantum efficiency of 1.25%. This is going to require a lot more modification and experimentation with the processing conditions. Quen Yuen at University of California at Santa Barbara has another small molecule system, and she recently reported efficiencies on the order of 3%. So there's some really interesting possibilities for small molecules. They're easier to make, easier to purify, easier to handle. So let's sort of review where we are in this whole organic photovoltaic quest. So capturing the maximum solar output, I think we know how to do that. And ANSER's got just the right kind of quantum chemists to help the synthetic people, to guide them. Okay, create long-lived excitons. Well, I think that's going to be a challenge, but I think there's some chemical and environmental architecture ways to do this and efficiently split them. And Mark's got some really, his smart matrix idea is, I think, really, really attractive. High hole and electron mobilities, because if you can't get them away from where they're formed and get them to the electrodes, you get a real problem. And I'll say something about that, a little more about that in a minute. And then the other is efficiently extract the charge at the electrodes to get them across these interfaces. I think we've made some advances there. and then finally to carry the charge away. And this at first may seem like something very trivial, but let me say something about that at the very end. So this is just so this is where we were before. One study that Mark and I and John Servetus have done, and this is a modeling study, and we can get into details in the questions and answer. It basically uses the Shockley equation, says that if you could reduce the exciton binding energies, if you could have them, for example, you could get to 15%. All other parameters, this is a modeling based on the nickel oxide cell I showed you. We can fit that data on the nose. We can show that we've extracted almost all the carriers that it will give when it's in that state. But if you could reduce the exciton binding energy, it starts looking interesting. Another thing has to do with the transparent electrode, the ITO. We pointed out that indium is very scarce, but when you build a cell and you try to make it larger and larger, I mean, the cells in our lab are very small. As you make it larger and larger, you're faced with how to get the current out, and normally that's done by putting silver bus lines on. Well, silver is not an earth-abundant element, the last time I looked, and so suppose you could have a more conductive TCO. And so these are just some plots. So if I have a cell at an ITO conductivity of 12% for a very small cell, to make it a large cell, I've got to dramatically increase the conductivity of the transparent conducting anode, or I'm in big trouble. And so I can gain a lot. And so these are different families of curves. If I have a 12% cell, then I can get good efficiencies with a poorly conductive TCO. But as I start making the cell larger and larger, I can't hold that 12.5% unless I go to higher and higher conductivities. So to point out, I think the record TCO conductivities in the country are from Northwestern, and there's one of Bob Chang's that has a slightly larger band gap, tin-doped cadmium oxide, and then CIO is one of ours, not CIA, but CIO, and we've measured as high as 17,000. So there's some really interesting possibilities for alternative TCOs. And finally, what about maximizing the carrier mobility? There are people who feel very strongly that that's one of the limitations, because if you can't get the carriers away, the exciton will recombine. And so these are the kind of mobilities we've seen, we meaning the community, have seen for bulk heterojunction photovoltaic materials. But now let's look at the kinds of materials that people are making organic transistors out of. And so, for example, there's small molecule single crystal organics that have mobilities of 15 centimeters squared per volt second and higher. They're vapor deposited films. We've made some in my lab where you can get 3 centimeters squared per volt second. We've spun cast molecular thin films. These are field effect mobilities of at 1 centimeter squared per volt second. And so you can see these are 3 to 4 orders of magnitude higher. And recently, work from Tony Facchetti, Mike Wasilewski, and myself, we've printed air-stable N-type semiconducting polymers, and these are printed by gravure techniques, inkjet techniques, and mobilities, I think not 1, but 0.85 centimeters squared per volt second. I can't say indefinitely stable in air. I can only say a couple years, because that's all we've measured so far. But one of the historic bugaboos and worries of the organics is, oh, they're not air stable. I think that's just a matter of molecule engineering. I mean, some of the organics that Harry showed us, copper phthalocyanine, you can sublime unchanged at 1,000 degrees C. It's used in automotive paint. Some of the materials that Mike Wasilewski is using, the perylene diimides, are used in automotive paint. So we shouldn't think that all organics are fragile, all organics are air sensitive, all organics are going to self-destruct. And I think that is cause for a lot of optimism. And finally, then you say, well, in a photovoltaic context, how would you really get the kind of carrier mobility you want? So one of the things we're proposing in ANSER, and this will be Lynn and Mike, myself, Mark, are going to be working, looping you on designing self-assembled structures where there's a high level of organization between the electrode, and of course the top thing on the electrode is going to be the kind of templating injection layers that I showed you already that will then template the growth of these kinds of self-assembled structures. So that's the game plan. So some conclusions, at least for this lecture, I tried to give you a picture of interfaces in organic photovoltaics. We don't understand everything, but we've learned some things. And we learned that you can increase the efficiencies. It involves increasing the carrier lifetimes, preventing quenching at the interfaces with the electrode. And you don't have to put up with PDOT anymore. You can pour it. I was going to say you can pour that bottle down the sink, but you don't do that. You put it in the organic waste container. And we've gotten record efficiencies. Well, so then you say, well, printing organic electronics? Whoever imagined that? Well, I should point out that there's a whole industry doing just that. So, for example, Plastic Logic has a factory in Dresden that by the end of the year is going to be making displays for Kindle-type ebooks. And the factory's geared up to make 1.2 million displays per annum. So there's lots of experience printing transistors. This is a burgeoning industry. If you can print transistors, I think it's going to be even easier to print solar cells. And what are you going to do with them? Well, I think probably the first applications are going to be more niche applications before we, Harry's Army puts them all over Arizona, Colorado, or wherever. But I think everything from, little chargers for cell phones and iPods. There are not a lot of electrical outlets in the third world. All sorts of flexible solar cells for, say, tents and other kinds of living places and backpacks. For any place where you need remote power, cheap solar cells are very, very attractive. And finally, so who did this work? I didn't do it all myself. I didn't do very much of it, in fact. A really talented group of graduate students, and a number of these, it's a Northwestern tradition, are joint with another faculty member. So the students are forced to cross disciplines. So that includes Brooks Jones, Tina Lee, Sheila Romanon, John Servetus, and Ben Lever. And then none of this would have been possible without some really enthusiastic and patient colleagues in a number of departments at Northwestern. I think we have chemistry, material science, and physics represented here. And then very fruitful collaborations with NREL and the Air Force Materials Lab, and some people who are willing to write checks. I think that's the last one, or just some pictures. So I guess we have time to show the pictures, do we? So here's Sheila, here's Junlu, here's Alex Martinson, Alex Haynes, now postdocing at NREL, Michael Irwin, ready to head off to BP Solar, Ahmad Timosina, a first year, here's Tina, Norma Sosa is just about to head off to IBM, Assunta Marachi is a collaborator in Italy, here's John Servetus, Justin Douglas was an REU research for undergraduates with us last summer. He's an undergraduate at MIT, really bright kid. So with that, I want to thank the organizers for inviting me, and thank you for your attention. So thanks very much.
Time for questions. One question and one comment. With that electron blocking layer where you've done the cross-linking, does the cross-linking improve the whole transport as well as improving the electron blocking? And
we have to make a whole. We haven't done that. That's a really good thing to do. We know the whole mobility, but I should mention. Let me put these down. I need both hands to do this. The FET experiment, of course, measures the mobility in the plane. And what we're really concerned with a solar cell, of course, is perpendicular to that. So we should do the hole-only device. We haven't done that yet.
The other part is kind of relating the first part on LEDs and the part on photovoltaics, because photovoltaics produce direct current. And yesterday and this morning we heard about problems with getting electricity on the grid. But if you go, say, to the next generation of solid-state lighting and such, a lot of that will be LED based. Do you think that one of the directions is going to be more towards direct current systems?
For the LEDs?
Well, you have the whole integrated system, because you talked at the beginning about building, integrating your photovoltaics in the building. And then if you just had photovoltaics and a storage device and LED lighting, it would seem that would be quite...
Yeah, I mean, that's interesting. So on top, right, so on top of the building you have solar cells, and then the electricity is funneled down to the basement or wherever you need lights, and have that all integrated. I really hadn't thought about that. That's a really interesting question, but I'm sure there are engineers who have.
Okay, thanks.
Tobin, that was really impressive. I have a quick question concerning the sheet resistance in the ITO. So you mentioned the cadmium dope system. Of course, with cadmium, you get nervous about toxicity.
All right, let me say something about that.
Okay.
And because it is, I'll say two. One is just a joke, but the German government actually has permitted the fabrication and widespread installation of cadmium telluride solar cells. This is First Solar. And the reason is the production cost is so low. The laws in Germany are their individual people are not going to be allowed to own them, because the idea is to recycle them, of course. But the idea is, for example, the new Hauptbahnhof in Berlin is coated with CadTel solar cells. And they're about 10% efficient. They're not as efficient as silicon, but much, much cheaper to produce. And so you've got to have them encapsulated. Okay. So cadmium, obviously, we're all worried about. On the other hand, when we work with it in my group, the health people here asked the students involved to have a urine test once a month, which they didn't like, but they agreed to do. But they were warned, whatever you do on that day, do not drink coffee before the test. And one of the students said, well, why is that? And they said, well, because coffee has so much cadmium in it. So I don't know. And all these fluorescent lights have mercury in them, right? Little drops of mercury.
Right. So the question I wanted to know is, what's the doping level of cadmium in the ITO and how does that correlate with the sheet resistance?
It's indium-doped cadmium oxide. It's got a rock salt structure. There's about 3 or 5 mole percent indium in there. So it's not a lot. Right. And the best conductivity we've had is 17,000 Siemens per centimeter. So that's, I don't know, it's a sheet resistance of about 1/3 that of the best. The best ITO you can get has a sheet resistance of about 10 or 12, if you know of any better than that. But a lot of them are more like 20. I mean, what you find is commercial ITO varies enormously in quality, in sheet resistance, and some of it is just really awful. Yeah. And I think it's mainly made by sputtering. The targets are about 4 feet wide by 8 feet long and a foot thick. So it's done on a huge scale, but I don't think it's done very carefully. And in fact, a lot of the reasons you use PDOT one theory is there's spikes in the ITO. And so you slather on a thick layer of some organic and you tenuous to smooth it out. The best studies that have been done of ITO, I think, are probably Neil Armstrong's. And he claims that something like 80% of the surface area of commercial ITO is completely insulating and dead. And we've done some similar things with Mark Hersom conducting AFM. And then there's some very nice work, conducting AFM work on PDOT by David Ginger at the University of Washington. And he also concludes a large percentage of the PDOT surface is dead. Wow. So you've got something dead on top of something dead. You're lucky you get dead the efficiency squared. You do. But if we really are going to go to higher efficiencies, at some stage we're going to have to worry about things like that.
Thanks.
And or lowering the costs.
Okay, if that's it, let's thank Tobin again.
Thank you.